In this lesson, we are working on optimization in calculus. In optimization, we are usually dealing with a real-life scenario that can be formulated as maximizing or minimizing a function with possibly having some restrictions. Let's have a couple of examples to understand it. Find the positive number that exceeds its square by the greatest amount. If x is a positive number, then the amount that it exceeds its square is x minus x2. Therefore, the problem can be stated as follows. Find x in the interval 0 to infinity that maximizes the function y equals x minus x2. What we do, we find the derivative of y with respect to x. We set it to 0 and we find the critical number. To classify this critical number as maximum minimum, we can use first derivative or second derivative test. Use first derivative test. At 1 over 2, the derivative is 0. Less than 1 over 2, when x is between 0 and 1 over 2, derivative is positive, therefore function is increasing. And after 1 over 2, derivative is negative and function y is decreasing. Therefore, at x equals 1 over 2, y is maximum. In other words, 1 over 2 exceeds its square by the maximum amount. Next example. Find the maximum area of a rectangle having base on the x-axis and upper vertices on y equals 12 minus x2. If we call the dimension of the rectangle 2x and y, since we have symmetry, we used x to the right and x to the left and one dimension 2x. Then we wish to maximize a equals 2xy, the area of the rectangle. This can be written as a function of x equals 2x times 12 minus x2, since x and y is the point on the parabola, which is the same as 24x minus 2x3, and x is greater or equal than 0 and is less than square root of 12, which is 2 root 3. X cannot be more than the x-intercept. Therefore, we are looking for maximum of ax equals 24x minus 2x3 on a closed interval. The derivative of the function is 24 minus 6x2. If we set it to 0, 6x2 is 24, x2 is 4, x is plus or minus 2. Minus 2 is not acceptable, x is 2. We find the value of area at 0, 2, and square root of 12. At 0 it is 0, at 2 it is 32, at 2 root 3 it is 0. Therefore, the area of the rectangle is maximum when x is 2. That means the dimension of the rectangle are 4 and 8, and the maximum area is 32. Next example, find the area of an origami box that is to be made from 8 by 15 centimeter piece of paper by cutting 4 slits from 4 corners and folding them up. We are basically looking for the value of the slit length that maximizes the volume of the box. If we draw the box, we see the height of the box is x, and the dimension of the base of the box are 15 minus 2x by 8 minus 2x. This means volume as a function of x is x times 15 minus 2x times 8 minus 2x, and x must be between 0 and 4. Notice that we cannot cut more than 8. We find the derivative of v at x. We can use product rule or expand it and take it the derivative. If we take the derivative and put it in factor form, the derivative is 4 times 3x minus 5 times x minus 6. If we set the derivative to 0, x would be 6 or 5 over 3. X equals 5 over 3 is the critical number. We find the value of volume when x is 0, 4, and 5 over 3. When x is 0, volume is 0. When x is 4, volume is 0. And when x is 5 over 3, volume is 5 over 3 times 8 minus 10 over 3 times 15 minus 10 over 3. This number is obviously positive. Therefore, x equals 5 over 3 makes function Vx maximum. In other words, the maximum volume is obtained by making the slits 5 over 3 centimeter long. Thanks for watching.